The main reaction in Chapter 15 is called electrophilic aromatic substitution. We abbreviate this often SEAR. Some of my students call it SEER reactions. So SEAR, substitution electrophilic aromatic, and that's where you get that abbreviation. Very similar to SN1, SN2, where you have substitution nucleophilic and unimolecular and bimolecular. So that's where that shorthand comes from. So if I take benzene and I react it with an electrophile, then as I stated previously, that means that benzene is behaving like a nucleophile. And so the electrons in the highest molecular orbital are going to attack the lowest unoccupied molecular orbital of the electrophile, right? So you have this HOMO-LUMO interaction. We know that that the highest occupied molecular orbital, though, of benzene is actually lower than your typical pi bond, and therefore much more stable than your typical pi bond. But if conditions are right, it will react with an electrophile, and we'll talk about those conditions throughout this section. And so you get, again, donation by pi electrons to the electrophile, breaking another sigma bond, right? And so the electrons then reside onto Y, whatever Y is. And you end up with this particular intermediate, a carbocation intermediate. And this carbocation is a special type of carbocation called the cyclohexadienyl carbocation. And so you see that it has some allylic carbocation characteristics. And then, of course, we get Y minus. So let's take a look at that carbocation, and we see that we could draw resonance structures, right, of the carbocation, just like we can draw resonance structures of allylic carbocations. And so I can move the pi electrons that are adjacent to that carbocation, and I get a second resonance structure where the positive charge is now distributed on that carbon at the bottom. And now I see that I have almost a diallylic system, but I can draw another resonance structure donating a pair of pi electrons again, and I get a third resonance structure. So these three resonance structures combined, we can kind of visualize what's going on. We see that the carbocation, that positive charge, resides on three different carbons, right? This particular carbon where I put the red dot, this carbon, and this carbon, right? So there is a positive charge, a partial positive charge, if you want to think about it that way, at those three carbons. And so in essence, you're distributing that positive charge between those three carbons. We often think about it as this, where you have this partial positive charge on each three carbons. That is the sum of those three resonance structures. And so this is really a better representation of the cyclohexadienyl carbocation. And we're going to kind of use this abbreviation as we go along, but you should be able to draw all of the resonance structures in any mechanism that we talk about. All right, so let's take a look at what happens when this intermediate forms. So I've drawn the cyclohexadienyl carbocation intermediate, and of course we know that we also generate Y minus, which is a nucleophile. It's also a base. So how is it going to behave? Well, we've seen with addition reactions of alkenes that if this were a typical alkene, the Y minus could simply add to the carbocation, and you would get an addition reaction. This is a typical reaction of an alkene. Now, because there's resonance throughout, you could also envision this carbocation also reacting with Y minus, just like we saw with allylic systems, right, where you could get one or two products based on resonance structures. And of course, if Y minus attacked this carbocation, then we would get a 1,4 addition. So it's almost very similar to 1,2 and 1,4. But notice something very important. When we go from this non-aromatic cyclohexadienyl carbocation intermediate to the following structures, I'm producing non-aromatic products, right? So these are non-aromatic products. The third possibility for Y minus is that instead of attacking a carbocation, it actually simply removes a proton, and the pair of electrons from that carbon-hydrogen bond then go back into that ring. You generate a new pi bond, and so notice here I have generated an aromatic compound. So I'm going from initially benzene, an aromatic compound, through a cyclohexadienyl non-aromatic carbocation intermediate to an aromatic system. And so we see that this last reaction is the mechanism that takes place instead of the previous two reactions. And so we're forming this aromatic system, and of course you notice HY is formed in the process. All right, our first reaction involving substitution is deuteration of benzene. If I take benzene and I react it with sulfuric acid, I see no observable change in the reaction because I'm simply substituting a hydrogen for a hydrogen. But if instead I use deuteriosulfuric acid, I get substitution of a deuterium, so I get deuterium benzene. And if we think about the mechanism of this reaction, we see that benzene again is the nucleophile, the deuterium sulfuric acid or deuterated sulfuric acid is the electrophile. I'm highlighting a hydrogen on that benzene because in essence we're going to substitute that hydrogen for deuterium, right? And so let's think about the mechanism. We know that benzene's a nucleophile. We know that deuterated sulfuric acid is an electrophile. We get pi electrons attacking the deuterium, breaking that deuterium oxygen bond. The electrons go to the oxygen, and this results in that carbocation intermediate. Okay, so we also get deuterated deuterated hydrogen sulfate anion from that as well. So let's take a look at, let's see if we can draw the resonance structures of that cyclohexadienyl carbocation, right? Remember, 3 resonance structures, and I'm going to show you a couple of times how to do this, and then, you know, hopefully you can figure out how to do this with all of the other mechanisms. So again, we're going to donate a pair of electrons from that pi system, from the pi bond to the carbocation, and we get another carbocation, right? And then we can donate the pi electrons from the top one, and we get our third carbocation. So these are the 3 resonance structures. Now, if I take that cyclohexadienyl carbocation and I react it with the conjugate base of the deuterium hydrogens, the deuterated sulfuric acid, then what's going to happen? We know it behaves as a base, not as a nucleophile, right? The driving force for this is that formation of the aromatic system again. And so it's going to remove the proton, the electrons go back into the ring, and you reform benzene ring, the aromatic system, and now there's deuterium that's been substituted for that hydrogen. And of course now we have monodeutyrated sulfuric acid that's generated as well. This is how you make deuterated benzene. Now, If we have an excess amount of deuterated sulfuric acid, then we can actually substitute for all of the hydrogens. So if I take benzene and I treat it with an excess amount of D2SO4, then the product here is, instead of only one deuterium on the ring, I can actually put 6 deuteriums on that ring. The second reaction we're going to look at is called sulfonation of benzene. Here, if I take benzene and react it with fuming sulfuric acid, there are many names to fuming sulfuric acid. Sometimes it's called oleum. Sometimes it's actually called SO3, H2SO4. So you might see different types of combinations in terms of reagents. And so when I use, this is very different than normal concentrated sulfuric acid. Fuming sulfuric acid, when you open it up, it emits orange fumes, gaseous fumes, and it's quite a pleasure to work with. So understand we're not just using sulfuric acid; we're using oleum as our reagent. And when we react benzene with oleum, we get this product, and this is called benzene sulfonic acid. Right? So we can now make benzene sulfonic acid derivatives, right? And if we think about the mechanism of this reaction, we have to think about what the electrophile is. We see, the grand scheme of things, benzene is always going to be the nucleophile with these types of reactions. And so one of the kind of difficulties is understanding what the electrophile is at times. With this particular reaction, the electrophile is sulfur trioxide. And so the structure of sulfur trioxide looks like this. It's in essence dehydrated sulfuric acid. If you think about sulfuric acid losing water, you get sulfur trioxide. And this is the particular electrophile. And so the mechanism of this is we're going to take benzene, we're going to react it with our electrophile, in this case sulfur trioxide, and of course you see that the sulfur has 3 oxygens withdrawing electron density away from that sulfur, and so it's taking on a partial positive charge, right? And it's actually very electrophilic. It's seeking out electrons. So benzene provides those electrons through the pi system, and when a bond formation occurs, we see that a bond breaks between the sulfur and one of the oxygen double bonds, and you're going to get a negative charge on that oxygen. So we get this species right here. Again, notice we're forming the cyclohexadienyl carbocation, right? And now we've placed this SO3 minus substituent onto the ring. Again, thinking about the resonance structures of that cyclohexadienyl carbocation, we know there's positive charge in these 2 positions as well. All right, so what happens next? Well, there's 2 things that have to happen here. The first is deprotonation and reforming the benzene ring, and the second is protonation of that SO3 minus. So we can use another molecule of sulfur trioxide. Sulfur trioxide is also a base as well, and it can abstract that hydrogen, and the electrons from that carbon-hydrogen bond go down into the ring, again reforming that benzene aromatic structure, and the result is this. So now I've formed my ring, and I still have SO3 minus, so I still have an anion. But notice when sulfur trioxide reacts with, removes that proton, I'm protonating it, which I form an acid, and so I can use this acid to then protonate the SO3 minus on the ring, and I get my benzene sulfonic acid, and I'm regenerating that sulfur trioxide. Now the cool thing synthetically, and we're going to see how this can be utilized later on, is that sulfonation is actually reversible. So if I take benzene sulfonic acid and I treat it with water and I heat it up, I can actually reverse that reaction completely and I can regenerate benzene. This is useful for synthetic purposes that we'll see later on. The third reaction is nitration of benzene. So if I take benzene and I treat it with nitric acid in the presence of sulfuric acid, I get nitrobenzene. So there's an NO2 group that goes on to the ring. And these yields are actually very good, upwards of 90% to almost quantitative. Now the question here is, well, what is the electrophile? How does NO2 get onto the ring and where does it come from? And if we think about the, what we have in that solution, we have nitric acid. So here's the Lewis structure of nitric acid, right? Nitrogen is double bonded to one oxygen. It has a single bond to two oxygens. Hydrogen is on one of them. So one of the oxygens has a negative charge and the nitrogen has a formal positive charge. And when I react, so I also have sulfuric acid in there. And sulfuric acid happens to be the stronger acid of the two, right? I have these two acids. So in essence, nitric acid behaves as a base relative to sulfuric acid. And I can protonate the oxygen that has a hydrogen already on it. And, so why would that happen? Well, think about leaving groups, right? We know OH is a poor leaving group, but when I protonate it, it makes it a good leaving group. And this is exactly what's happening here. So the OH gets protonated, and I form this structure, right? Again, the oxygen on the left has a negative charge, nitrogen's positive charge, but now the oxygen has a positive charge because there's another hydrogen on it. And so I can see that I'm forming a good leaving group here. And of course, I also get hydrogen sulfate anion associated with it. So now what happens? Well, this protonated version of nitric acid is now going to, so the negative oxygen can donate a pair of electrons onto the nitrogen and kick off water. The result is I get this species. So notice nitrogen still has a positive charge on it. It's now has two oxygen double bonds connected to it, right? And the oxygens are neutral. This is called the nitronium ion. And in terms of electrophilicity, we see the nitrogen has a positive charge, a formal positive charge, and it is electron deficient. So it's seeking out electrons, meaning it's a good electrophile. Benzene will react with that nitronium ion, and it will react with it at the nitrogen. A pair of pi electrons, right, attacks the nitrogen, and of course nitrogen can only have 8 electrons around it, and so we have to break one of the nitrogen-oxygen double bonds by placing a pair of pi electrons onto the oxygen. The result is a structure that looks like this, where nitrogen again still has a positive charge. Now one of the oxygens has a negative charge, right? The one that accepted the pair of electrons has a negative charge, and then the other oxygen still has a double bond to nitrogen. And of course we're creating the cyclohexadienyl carbocation as well, which again is stabilized through resonance, placing a positive charge on these two carbons as well. Now, what happens next? Well, we now have our cyclohexadienyl carbocation, so I need to deprotonate it. I can use water that's generated from the dissociation of that protonated nitric acid, right? And I can use that as a base, and it's simply going to remove that proton. The electron's going to go into the ring to reform the benzene ring. And the result is nitrobenzene plus the hydronium ion. Now, because the nitronium ion itself is the electrophile, you can also buy nitronium salts because the nitronium ion is relatively stable as a cation. And you can see this here in the following reaction, where benzene reacts with nitronium tetrafluoroborate at minus 20 degrees. So in solution, these are very reactive ions, and you get nitrobenzene. And again, the yield is very good, around 87%. So this is an easy way. You don't have to necessarily use strong acids, and you get the same results. But again, you have to run these typically at lower temperatures. Our fourth reaction, the electrophilic aromatic substitution reaction, or Sears reaction, is halogenation of benzene. So if you recall, if I take benzene and I react it with a halogen, unlike alkenes that would undergo addition, benzene doesn't react with halogens. However, when I take benzene and I react it with a halogen in the presence of a Lewis acid, such as iron halide, right? So we have ferric halide present. I get a substitution reaction. So again, it's still not an addition reaction like an alkene would behave, but a substitution reaction. And a byproduct of this reaction is HX. Now, in this type of reaction, the halogens that we can use really are limited to chlorine and bromine. Fluorine is too reactive, iodine is not reactive enough. So we're limited to chlorination and bromination. And if we think about, again, the mechanism of this reaction, why does bromination, typical bromination yield no reaction, but bromination in the presence of FeBr3, for example, yield a reaction? Again, it has to do with the stability of that benzene ring. And a halogen is simply not a good enough electrophile. So we have to increase the electrophilicity. In the previous examples that we saw of benzene reacting with an electrophile, these were good, strong electrophiles, right? Very electron deficient. So here I have a situation where bromine itself, by itself, is not a good electrophile. But bromine will react with iron bromide. And iron bromide is a good Lewis acid, meaning it will accept electrons. So if ferric bromide is a Lewis acid, that means bromine is a Lewis base, and it can donate a pair of electrons into the iron, right? The result is you get this Br, FeBr3 complex, where now bromine has a positive charge because it's donated a pair of electrons to the iron metal, and iron has accepted more electrons, and so it takes on a negative charge. This is called a Lewis acid-based complex conjugate. It is this Lewis acid-base complex conjugate, FeBr3, that reacts with benzene. And you might say, well, how does this reaction occur? So notice what's happened to that bromine part. The bromine that's attached to the iron has a positive charge to it. So it's now withdrawing electron density. You might think that that benzene will attack that particular bromine with the positive charge, but in fact it's actually going to attack the bromine at the end simply due to steric effects. And so what we have is we have a donation of a pair of electrons from the pi system on benzene to that terminal bromine, And then the electrons from that bromine-bromine bond certainly are weakened, right? Because that bromine that has a positive charge, the middle bromine, is attracting electron density, and so those electrons then go to the bromine, and the result is you have now brominated the ring and created this cyclohexadienyl carbocation. Again, thinking about resonance, uh, it's going to be stabilized by redistributing that positive charge. You also generate FeBr4 minus, FeBr4 minus. And so what happens now is that iron-bromine bond breaks. You're essentially releasing free bromide ions, and those bromide ions can then remove that proton, so they're acting as a base. They remove the proton. The electrons from that carbon-hydrogen bond then go into the ring, just like we've seen previously, and it yields bromobenzene, right? We also generate HBr, and we're regenerating that ferric bromide ion as a catalyst.